Bismillahirrahmanirrahim. Let's start the salient pole synchronous machines. In chapter number 4, we discussed and derived equations for power and torque for a synchronous machine, but that was a cylindrical rotor machine, and we ignored the effect of saliency of rotors in that chapter. In order to understand the effect of salient pole machines, or in order to understand the effect of saliency of the rotors, let's see the figure C1, C.1. So this figure shows a salient pole synchronous machine. As you can see that the poles are salient, a salient rotor has been used. Now if a three-phase supply is provided to the stator, then a revolving field will be produced because of the three-phase supply provided to the three-phase armature winding. Let's assume that the revolving field is revolving in counterclockwise direction. The rotor has not been energized, so we can assume it that it will simply a piece of iron that is placed in the space in the stator. So we can see that because of the small air gap at this side along the direct axis of the rotor, it is easy to establish flux along this direction as compared to establish flux along this direction, which is perpendicular to the polar axis and which has a very large air gap. Larger the air gap, larger is the reluctance, and difficult is to establish the flux. So the magnitude of flux in this direction will be less as compared to this direction where it is easy to produce the flux because of the small air gap. In cylindrical rotor machines, since the air gap is uniform, so no such problem or no such phenomena exists in cylindrical rotor machines. There are some definitions. Introduction of the direct axis or magnetic axis or polar axis. So the once we energize the windings of the rotor, here we have assumed that the rotor windings have not been energized. Once the rotor windings have been energized, it will behave as a magnet. Then these sides will act as poles of the magnet. Let's assume that this is the north pole and this is the south pole of the rotor magnet. And then basically this is the magnetic axis of the rotor, or it is also known as polar axis because the poles are established along this axis, and it is also known as direct axis. Perpendicular to this axis or the quadrature axis, it is termed as quadrature because it is perpendicular to the direct axis. It is also termed as magnetic neutral axis because there is magnetic neutral region, magnetically neutral region at this axis. It is also termed as interpolar axis because it is between the two poles and it acts as a magnetically neutral region. So let's discuss the equivalent circuit of a salient pole synchronous machine. We discussed the equivalent circuit for cylindrical rotor machine, and we observed that it consists of different components. For example, the internally induced EMF EA, the reactance representing the armature reaction of the generator, the inductance of the winding due to leakage flux, the self inductance, and the resistance of the armature winding. In salient pole machines, the factor 1, 3, and 4 will remain same. Only factor number 2 will change, and it requires our attention. There are changes in the armature reaction when the cylindrical rotor is replaced by a salient rotor machine. So figure C2 shows a two-pole salient rotor rotating counterclockwise within a two-pole stator. The rotor flux is called VR and it points upwards as we can see here. that we have a rotor. It is rotating in counterclockwise direction. Now it is assumed that the rotor winding has been energized. In the previous figure, we assumed that we provided a three-phase supply to the stator which produced a revolving field, and we were observing that it is easy to produce flux in certain direction as compared to certain other directions. So we were trying to understand that why the salient pole machines are treated separately as compared to cylindrical rotor machines. Because of their non-uniform air gap, the flux is easy to establish in certain directions as compared to certain other directions. Now we are treating this machine as a generator. The rotor winding has been energized and it is rotating in counterclockwise direction. The rotor is rotating in counterclockwise direction and the machine is acting as a generator, so it means that some voltage will induce in the armature windings. Let's see what is the direction of the voltage induced in the armature windings. At this particular instant of time, the field of the rotor is pointing upwards. So this is acting as a north pole, this is acting as a south pole. So first of all, we will try to fit the condition according to the definition we are familiar with. So we are familiar with the definition of voltage induction, that when a conductor is moved in a magnetic field, voltage will induce in the conductor. Now here we can see that the conductors are stationary and the field is rotating in counterclockwise direction. So it is similar to the situation that if the field is stationary and the conductors are rotating in clockwise direction. So the direction of relative motion between the field and the conductors is basically in clockwise direction. Assuming that the field is stationary, the conductors are rotating, the direction of relative motion is clockwise, the field is pointing upwards, then we will apply right hand rule to find the direction of the voltage induced, and if the circuit is closed, the direction of current flow. So the thumb points in the direction of relative motion, the first finger points in the direction of field, then the second finger will point out of the paper in the direction of the voltage induced. So the direction of voltage induced is shown here, out of the paper in these conductors and into the paper in these conductors. Now as the conductors at this location are cutting maximum flux, so it means that voltage induced in these conductors will be maximum. So this is the plane of EA maximum. Maximum voltage is induced in these conductors that are directly under the action of the poles. Let's assume that we put some load on the generator having lagging power factor. Some lagging load has been introduced at the generator terminals. So it is shown here by a current IA which is lagging behind the voltage EA, the induced EMF EA. So the current IA is lagging behind the voltage. It means that a lagging power factor load has been introduced at the generator terminals. This lagging current IA or this armature current IA will produce a stator magnetomotive force or stator MMF. Since stator consists of winding, armature winding, or in other words number of turns, and since current is flowing in these turns, so we have product of ampere and turns. That is why that is stator magnetomotive force, because the current is flowing in the stator windings. So we can say that the stator magnetomotive force is produced because of this current IA. Now, this current can be resolved. This stator magnetomotive force can be resolved in two components. One which is directly along the rotor axis, or in other words, the direct component of the magnetomotive force, and the other one which is acting at an angle of 90 degrees, or which is acting along the quadrature axis of the rotor, which is termed as the quadrature component of the magnetomotive force. Now, these stator magnetomotive forces will produce stator magnetic fields. This will produce BS. This magnetomotive force along the direct axis will also produce a magnetic field BD, and this one also produce a magnetic field BQ. Now you can see here that it is easy to establish flux in this particular direction, or it is easier to produce magnetic field in this particular direction because of the small air gap as compared to this particular direction where we have a very large air gap. So it will be offering high reluctance to the flux path. It means that the flux magnitude will be smaller along this side along the quadrature axis. Definitely, when the flux magnitude is smaller, the strength of the magnetic field or the magnetic field strength Bs will also be Bq will also be smaller as compared to Bd. This situation has been shown in the subsequent figures as we can see here. The stator magnetomotive force produced a stator field that can be decomposed into two components, BD and BQ. You can see here that the magnitude of BD is larger than the magnitude of BQ for the same reason that we have already discussed. We can see the flux magnitude that can be calculated here. It is equal to the direct axis magnetomotive force divided by the reluctance along the direct axis. Similarly, the quadrature axis flux is equal to the quadrature axis magnetomotive force divided by the reluctance along the quadrature axis. So since the reluctance along the direct axis is less than the reluctance along the quadrature axis, so it is easy to establish the flux along the direct axis. You can see the difference in the magnitudes BD and BQ, and because of this difference, you can also see that the field BS for salient pole machines is not exactly at 90 degrees with respect to current as it was the case for non-salient pole or for cylindrical rotor machines. So the dashed arrow shows the direction for the non-salient pole machines, shows the direction of Vs for non-salient pole or cylindrical rotor machines, while the solid arrow shows the direction of Vs for salient pole machines. And this difference in between these two is because of the fact that BD is larger than BQ. If we replace this salient rotor with cylindrical rotor, you will see that it will offer a uniform air gap. So BQ will be equal to BD. So there will be no need to discuss this particular theory for for cylindrical rotor machines because both the components will be same. So it is easy. So the flux established in different directions will be uniform because the reluctance offered to the establishment of flux in different directions will be uniform in cylindrical rotor machines. So this fact is also represented here for salient pole machines BS, BQ, BD. Now this magnetic field BD or this flux is cutting the armature conductors in this particular direction with maximum strength. So it means that it will induce voltage in the armature conductors that will be maximum directly under the action of the pole. And since this voltage is produced because of this direct axis magnetic field, it is termed as ED. Similarly, this field BQ will also cause a voltage to induce in the armature field. It is termed as E. In the armature conductors, it is termed as EQ. And the total output voltage V phase along the terminals will now be the phasor sum of EA, ED and EQ as it is depicted on the next figure. We can see here that EA, EQ, ED, their phasor sum is equal to V flux. Now, how can we represent this voltage or this voltage drop in the equivalent circuit of this synchronous machine? We can see here that this for the cylindrical rotor machines, the armature voltage E stat in cylinder. Just recall the discussion for the cylindrical rotor machine where armature current IA induced uh, the armature current IA produced a magnetic field Bs, which induced a voltage E state in the stator winding, and that was the voltage induced because of the armature reaction that was modeled for cylindrical rotor machines. Just recall that theory. So in case of cylindrical rotor theory, the armature reaction voltage produced was directly proportional to the stator current, and it was lagging behind the stator current by 90 degrees. Sorry. So in the same way, for salient pole machines, each armature reaction voltage is directly proportional to its stator component of the current, and it is lagging behind its stator component of the current by 90 degrees. So this fact can be modeled by assuming that the voltage ED induced in the armature windings is or is produced, or this component is due to a current ID, the direct axis current, direct axis voltage drop, we can say, is represented by a current in the stator winding, which is termed as direct axis current, and this drop is taking place across some reactance, which is termed as XD. Now, if the component ID is multiplied with the reactance XD, it will just change the magnitude of the phasor, and if we multiply it with the operator J, it will rotate it in counterclockwise direction by 90 degrees,